Okay, welcome everybody to today's seminar. Those who are in the room and those who are following us online. We have the pleasure today to have with us Dr. Vassiliadis, Dr. Dimitrios Vassiliadis, from the US, from the States. Dr. Vassiliadis obtained his undergraduate degree in the Aristotle University of Thessaloniki and then master and PhD all in physics from the University of Maryland. He joins the SWFO-L1 team in 2018, and he's currently scientist for this program, acting as the link between the operational space weather user community and the program office for the data products. Prior to joining NOAA, Dr. Vassiliadis was a research scientist with NASA Goddard for 15 years. His research focused on the Earth's magnetosphere, with topics ranging from solar wind magnetosphere coupling to the geomagnetic and ionospheric response to geoeffective structures such as coronal mass ejection, CMEs, to electron transport and acceleration in the radiation belts, working on data analysis, simulations, and predictive models. Apart from spending his time teaching at the University of Maryland and later at West Virginia University and Washington and Jefferson College, Dr. Vassiliadis had 2 space science experiments on the STF-1 CubeSat, a mission built by NASA's Katherine Johnson facility, and which was launched in December 2018, that remained operational for more than 5 years. Certainly the list of his accomplishments is long, but I suggest we give the floor to Dr. Vassiliadis, who will talk to us about the program CCOR-1 and the Lagrange Orbit Observatory. Please.
Okay. Thank you very much. Thank you very much. It's a pleasure to be here. Let me make some introductory notes. So first, let me double check that we're being listened to, heard rather, online. Can somebody? Yeah. Okay. Great. Thank you. I was thinking of speaking sometimes in Greek and sometimes in English. Actually, as much as in Greek as possible. Is that a problem, or should I just stick to English?
We are quite safe for the audience because from the names I see all our Greek speakers, but in general we have language English because someone can link later or can follow from the YouTube channel of the Academy, and then if he's not a Greek speaker, that will not understand.
So the majority will be in English. Okay, but I will interject some things in English. So again, thank you very much for accepting this very sort of impromptu kind of request. It's a visit to Greece that sort of suggested that. I will provide background for these new observations and for the missions that have been going on. So that they can motivate potential uses of the data here and elsewhere. Let me show the team that I work with, representing collaborators from the instruments that are participating on this program, and I will go into more detail about the instruments themselves. So these are from various academia and industry organizations in the US primarily, but also a collaboration with Europe. NASA Goddard support. Cursor here for several of these programs. We are very closely collaborating with NASA on several parts of this and other projects. And then, of course, NOAA Science, where we have support mainly from the science community within NOAA, but also from the forecast office at SWFO, Space Weather Prediction Center. So let me give a little bit of a perspective. Why are we flying these missions? What is the interest? And I'll give 2 perspectives, our primary one and then our one that might be called secondary, but actually it's also very close. So within NOAA, which is the agency within the US that is responsible for monitoring weather, παρόμοια με την ελληνική μετεωρολογική υπηρεσία, αλλά βέβαια με πολλές άλλες ευθύνες. and also for modeling weather and also monitoring and tracking space weather, obviously, as part of that terrestrial component. We have the responsibility then within the organization to provide measurements from the sun and from the space environment that will go to our main customer, which is shown in the lower left there. That's the view of the forecast office in the Space Weather Prediction Center in Boulder, Colorado. The images and data from our central star and from the planets and moons and other parts of the space environment around it are fed into the screens of forecasters and the models that they use in a 24/7 basis, and so they're important for their purposes. And as the sun waxes and wanes in its solar cycle, these effects become more or less important. So our first need is an operational one. But then, as this final schematically indicates, we have a transition of models from the research realm into the operational realm. So we have this, what's called research to operations, the R2O set of activities. So much about the operational needs. On the other hand, these missions provide us with very high quality data, as I hope to convince you in the next few slides. And so there's a second component there, which is the research significance of these data. And for that, we have the imperatives from the science community, for example, through their recent decadal survey that I'm pointing out in the lower left there for solar and space physics. This was released in December of 2024. And so the science community guides NASA primarily, but also our contributions to the need of observations around the sun in a sort of called 4-pi type of representation. So have as many observations from the sun as possible, not only in the ecliptic plane, but also from off-ecliptic perspectives. And similarly, for solar wind disturbances, shown schematically on in the two diagrams below, we have the emergence of what are called mesoscale observations, that is, phenomena that connect the large-scale disturbances, such as CMEs, for example, to the microscopic or more kinetic representations. And so these are shocks, this is the effect of turbulence, and these are sheaths, and so on, that I'll give some examples later. So within those research perspectives, it's understood that NOAA's missions can make significant contributions because, for example, the two missions I'll talk about are on the Sun-Earth line. They're on this critical axis of observations around which many other observations can be built. So they will provide the reference, the backbone, as it were. Similarly, for the tracking of CMEs, for mesoscale structures, and so on, our observations are from the Lagrange 1 point. And again, that's a critical point in our gathering of observations for the research community. Again, so these are the two large axes on which we built these programs. So the program I want to talk to you then about mainly is the Space Weather Follow-On, or SWFO, SWFO. This is a joint collaboration between two agencies, NOAA, that's leading it and funding it, and also NASA, which is technically responsible for many of its aspects. And it has the aim of providing these critical solar measurements for a very narrow, very well-defined domain, and also heliospheric data, that is solar wind data, to these types of users, to operational users such as forecasters that we talked about, and what we call retrospective users. These are the scientists, educational experts, and other sort of later users of the data. So we're operating from 2 points. I'll start first with the diagram on the right. So we have, I'll talk to you about an instrument, a coronagraph, an astematographo, which has been deployed at geo orbit, so relatively close around Earth at a fixed orbit. Oops, moved forward. And then another observatory, another mission, which is at the Lagrange 1 point between Sun and Earth at a relatively very useful, slightly unstable libration point which is between these two masses. And so from these platforms, we gather the data that we need. A schematic of the spacecraft that you'll see in more detail later is shown here. And we're, as NOAA, we're also responsible for developing ground segment networks, that is antennas and other processing centers, so we can take the data from space and deliver them to, as I said, to our users as fast as possible. The operational component is really the rapid delivery of data. So let's look at what observations we collect and how. These are the two coronagraphs that we operate. On the left is CCOR-1, compact coronagraph 1, that's that's operating from GEO. And on the right is the virtually identical CCOR-2 with a slightly larger field of view for longer tracking of CMEs. That's operating from SWFO-L1. On the right is a table with the main requirements for forecasting needs, notably the centering of the image, its orientation, how fast the data will be refreshed, which is 15 minutes, which is adequate time for modeling and forecaster needs. Importantly, the field of view, which is 3 to 22 solar Earth radii, similar to the overlapping largely with the LASCO C3 field of view, which we want to replace. And then for CCOR-1, for the geostationary placed coronagraph, we have a slightly different, smaller field of view, 3.7 to 17. This will be our backup capability. And a very wide range of intensities from 11 orders of magnitude of the mean solar brightness to 10 orders of magnitude below mean solar brightness. And the corresponding changes for the field of view change also the only other difference or produce the only other difference requirements, the resolution, which is slightly coarser for the smaller field of view and better for the wider one to keep the cost overall the same. Acquisition is of the order of 27 seconds, roughly 30 seconds, as we provide it externally. And then there is averaging of these images, as I'll tell you very soon, to avoid the effects of SEPs, solar energetic particles. And so these are the important measurements we provide within those needs. So on the right, we have a view of a comparison between the legacy coronagraph that we see on the left, the LASCO C3, and the new coronagraph on the right, operating on GOES-19 for an identical set of times. And we see that there's much better coverage, even though the field of view is slightly smaller. There's much better quality in the images from the newer coronagraph, and I'll go into a few details in a moment. So what does the new coronagraph provide us? It gives us an extended dynamic range compared to the new one, so we can detect both the very large events without saturating the image, and also the very faint features from which potentially new instabilities, new disturbances may be driven. We have a higher saturation threshold, so we don't have that bleeding or blooming effect that you see here with a very bright object, such as the 2024 comet Chushan Atlas. So we don't have these edges that are produced because of the CCD technology. We're using active pixel sensor technology, APS, so the saturation is less pronounced or does not exist. For solar energetic particles, we have a very different approach. You may all remember, probably, or those of you who are solar experts know the snow, the effect that solar energetic particles produce on coronagraphs in a transient manner, where the whole screen lights up with particles that hit the sensitive electronics of the detector. To avoid that, we have a periodic scrubbing for every single image that we produce. And the number of images that we average over ranges from 5 to 26, depending on the activity that's being detected. So that means that when we have significant flux of SEPs, we take the median effectively of a number of images on a pixel over pixel basis, and then we provide the final image, which is free and clear from SCPs to the users. And then the accuracy is also very high. This is yet another feature. This is a sub-pixel accuracy, less than half a pixel that we have there. There are also other advantages that we have listed on the right. So let me give you an example of how this instrument is used operationally and what the advantage is there in two very specific instances. So on the right, we see a very typical tool that forecasters at NOAA and also at NASA use, and also at other locations, where they combine images from of the same disturbance from several different vantage points, from several coronagraphs, in order to create a three-dimensional view of this object. This is the coronagraph analysis tool, for CAT. These two images here, the one on the left and the one in the middle, are both from the Sun-Earth line. One is close to the Earth. This is CCOR-1. This is on geosynchronous orbit, so that's the new instrument I was just talking about. And this is again the legacy instrument, C3, which is much closer to the Sun than GEO. That's at Lagrange Orbit 1. And what's not shown here is C2, a smaller size coronagraph that's placed also, that's part of LASCO as well. And on the right is COR2, which is on board stereo, which has moved away from the Sun-Earth line. It's now approximately 30 to 35 degrees to the west. And it's looking at the same disruption, the same explosion, but from the side, as it were, as it's heading towards the Earth. And the advantage of the new images is here. This series of squares indicate the numbers of images that are available at any given time, and the continuity. From these colors, which are denoting different coronagraphs, you see that all the legacy instruments have significant gaps that have to do either with the capabilities of the coronagraph itself or with the delay at which the images are produced and sent to the users. Whereas the last row there from GOES 19, from the new instrument, is continuous and can actually be used to obtain very steady rates of the emergence of this structure in time. So we can actually take time derivatives because we don't have to be concerned with any gaps. Whereas before, there was always a concern that some data might be missing. And so these time derivatives will allow us to track the object, as is shown here in this tool, and obtain features such as the position of the object, the speed in the plane of the sky, the mass eventually, which is a useful diagnostic because we'll extract the size and then calculate the density from the brightness. And so we can infer what the speed of the object is, the time of arrival at Earth, and other useful quantities. In a second example on the left, I'm showing also another part of the usefulness of the data. The top diagram there shows all of these diagrams show the delay, the so-called latency in delivering this data to the users. And we see significant latencies for LASCO C2 and C3. This is a logarithmic axis in Y. So we have very significant delays occasionally when the spacecraft is not able to send the data down. And so these delays limit the capabilities of our forecasters, and we want to reduce them essentially to zero, which is achieved here in the top diagram there with the new data. You see no gaps, first of all, and also everything is delivered at 15 minutes as promised. The small gap that you see there is due not to the spacecraft, but due to ground processing. So again, some good evidence that those data are ready to be used by forecasters and researchers. And then as we go now from operations to research, before I shift gears a little bit and talk about the second part of the program, these are some research targets that I think solar, for example, people in the solar community will recognize. Importantly, the main goal, of course, is still tracking of geoeffective structures such as CMEs. This is the same tool that I showed a moment ago. There's a very similar tool developed by NASA, which is called the stereo tool, StereoCat. Very similar structure. You can find them now online, and there are Python versions, there are IDL versions, and so on. And then the community has now shifted also to, has been years working on automatic detection of CME. So in addition to having a forecaster or another specialist look at the images and infer where the CME is, we have algorithms that can do that in real time or offline. And an example is SEEDS from George Mason University, and there are other methods such as Cactus and CORIMP and so on. But there are now new tools, as I'm showing here, that apply, for example, AI, or in this case, computer vision. So these are more advanced techniques that will ideally enhance the current capabilities. And so with the new data, we expect to continue all the significant legacy from LASCO that has been going on for more than, for close to 30 years, effectively, and expand into new directions. As yet another example of research/operational objectives, we have the CME catalogs that that exist in the community. There's the NASA CME catalog shown here, or the SOHO LASCO CME catalog, curated by Goddard and NRL. But there are also other CME catalogs around the community. And so with the new data, we expect to be able to contribute to those and track the solar activity over years. Now, going from the very large scales to the small scales, still very important, I think, research objectives is to track, as these examples show, features in the solar atmosphere, in the outer part of the solar atmosphere. This is close to the sun. These are observations from Parker Solar Probe, from a paper by Nindos et al. And on the right is an example from STEREO, where we have the same method now applied much further away from the sun, much closer to the sun, I'm sorry, with the COR-2 coronagraph. Both methods aim to represent very small features, in contrast to the CMEs that I was talking a moment ago about, very small features, and track the flow of these features as they move away from the sun, so that we can obtain the local velocity field. So use these features as trackers, as is done, for example, in atmospheric science by tracking clouds, for example, cloud formations, to obtain the wind speeds, and then feed them into tools that can obtain that can provide us both physics and also dynamic features of the process that take place deep in the solar atmosphere. On the top right is another research goal, which has been elusive so far. It's to identify the boundary between the very turbulent and intermittent boundary that exists between the outer part, the outer edge of the corona, and the beginning of the young solar wind. And that has been under debate for recent years with observations from other recent missions. But we think that in addition to LASCO, CCOR-1 and CCOR-2 soon can be used to obtain that boundary, because the field of view ends a little outside that the traditional estimation of the field of the boundary there. So in summary, the only other thing I would point to, this is a combination of slides, is a slide that I have here. So I would point, I think I've talked about all these, but one other item that I would mention here before we shift gears is that we're starting to see that the community is changing, is adapting its tools, such as JHelioViewer, that's shown here on the lower right, and other forecasting tools. This is a tool that I'm showing with the cursor that's being used in Goddard in their forecasting center, NASA Goddard, to include the new images of CCOR-1. So here's CCOR-1 next to an image. I think that should be LASCO C2, I think. And so they're using the new coronagraph, have been using for more than a year now, the new coronagraph alongside the traditional ones. So any questions up to this point? Because I'd like to shift gears a bit, if you allow me. Okay, so I talked about, yes, Stamati.
So what is the solar surface resolution of the latest coronagraph compared to LASCO, for example?
Right, so
how many arcseconds?
It's, as I showed, it's 50 and 70. for the solar atmosphere, right? For the solar corona, not for the solar surface, right? Yeah. So this is better than what LASCO had. LASCO C3 had 112, so it's about half as large. Now C2, the
C2
smaller,
like
C2 has a higher, has a higher, but we're not interested in the types of scales that C2 is observing necessarily. We do have an overlap, but the importance there is again driven by the needs of forecasters and how fast, how early we can detect these features so that we can extend them and drive the coronal models further out. So we're not trying to depict every single detail that we have, with smaller size coronagraphs. We can talk more about this in the sort of ground and space collaboration, because there are coronagraphs from the ground, for example, that can reach much, much closer to the sun. And so there is a very fertile ground for combining these observations, and people have started to do that as well. I'm not showing too many examples of this here. Between, let's say, the deepest observations of Mauna Loa Observatory and our observations, which start out with a much wider, radius. Yes, Jan.
So you mentioned the latency for CCOR-1, which is evident. I mean, since it's geo orbit, it's
right.
Much
latency
better.
Is very, very low.
What about the CCOR-2? Is there any?
Right. So the latencies there, no, they're identical, and they're driven primarily by CCOR-2. Go back a little bit. So the latencies are 30 minutes for both. Is it shown here? No, it's not shown here. So the latency is 30 minutes, but in practice, which of course is exceeded by far for GEO, but for CCOR-2, it's of the order of 20 minutes. So again, it's very, very fast. And for the solar winds, 5 minutes, right? So I'm going to talk about this in a moment. But for the solar wind, the latency is the requirement for the latency is 5 minutes. The actual performance, which is what actually is delivered to the users, is about 3 minutes.
Vassiliadis, do you know why? I mean, it's the same. They are with SOHO. They are practically the same place. Why did SOHO have this latency issues?
Oh, because it's because the networks that were used to support SOHO are not 24/7. Usually, so our networks have to be 24/7, so they're deployed around the globe, in the US, in Southern Europe, and also in New Zealand, Australia, and so on. So they have to cover these on a 24/7 basis. SOHO can use the DSN, which is also on a 24/7 basis, but that operation is very, very expensive. DSN is very expensive to use, and so in some intervals doesn't have the same requirement to support these observations, so therefore sometimes it does not.
So it's a ground support issue, not a spacecraft issue.
Not necessarily, no, because the encoding on spacecraft and the downlink is comparably fast. Yeah. So yeah. All right.
One more question,
Sure.
Dimitri. You mentioned. Are you finished?
Yeah.
You mentioned that you do corrections for penetrating protons on the CCD.
Ions, yeah.
And is that done on board? And how do you check the validity of that operation? Do you actually transmit the core data of the ground now and then to see that it's done correct?
That's right. There is a program that does that. So first of all, the answer to your first question, all of that SCP reduction is the cosmic ray scrubbing, as it's sometimes called, done on board. And then every so often, on a very infrequent basis, there are some raw data that are sent down to make sure that we do the right thing. Yeah. But that depends on the activity. Yes.
So these images are polarized light?
No, that's a great question. So all of these coronagraphs that I showed are white light, which is unpolarized. The new polarized images come from PUNCH, which is another NASA mission that was launched March of last year. And it's really, for solar physicists, it must be a great time, right? I mean, we have so many coronagraphs and so many other tools looking at the sun at this point, and we've added this polarized capability recently with PUNCH. Now from NOAA, we're actually funding a separate project for PUNCH, which is the transmission of a small amount of data in real time, whereas the bulk of the data will be delivered with very long latencies. We would like to see some data for training forecasters and training scientists within NOAA in real time. So we call that the Quick PUNCH project. And so within a few minutes, we have transmission of those images, and they have both the natural, the regular brightness, and also PP, the polarized brightness, right? So that we can develop the next series of tools based on the internal structure of CMEs. Yeah. Right. So we're talking about this anyway. I'll digress. At the end, remind me to tell you about the comparison of these measurements, because we really are at the stage where we can compare measurements from images in this case, but also in a moment I'll talk to you about measurements from several different missions from the same physical object. In this case, of the same regions of the solar corona. In a moment I'll talk about in situ measurements from L1. So let's go to L1. So this is our second component. Now this is an actual spacecraft deployed at L1, and I don't think I need to tell this audience about the importance of L1 as a vantage point. So in addition to the coronagraph that we have at L1, thanks to the recent mission, the same spacecraft is carrying 3 in situ measurements with the basic observational capabilities for the solar wind. On the left, we have the instrument measuring plasma properties. This is the solar wind plasma sensor, or SWIPS. It has a high heritage from NASA's IES for the Rosetta mission, and it's developed by the same group, SWIRI, and the PI is Rob Ebert. And so that will measure, as I'm going to show you, plasma distributions, and from that we'll extract moments, that is density, velocity, temperature, and so on. And in the middle is the suprathermal ion sensor. The question, how do we say suprathermal in Greek? Hyperthermikes. I'll leave that to you to consider. Okay, that's it. Homework. That's your homework. So suprathermal, so not quite the energetic region, but sort of the intermediate, the bridge region. And again, I didn't bring all these diagrams, but I think this audience understands what suprathermals are. And the heritage there is from MAVE and SEP and other, and actually it goes back all the way to Themis SST, the solid state telescope. And the PI there is David Larson. So we're collecting not only ions, as the name mentions, but also electron fluxes. So this is the replacement to ACE's very important instrument of EPAM, which is very heavily used within NOAA. And then on the right is the magnetometer, which is actually a suite. It has 2 sensors, as I'm going to show in a moment. The outboard sensor far from the spacecraft, and an inboard sensor closer, so that we can see what the effects of the currents of the spacecraft itself are on the measurements that we take on the outboard. And these deliver data based on these requirements. Importantly, for example, for the plasma, ranges of velocities, in situ velocities, that is, vectors, between 200 and 2,500 kilometers per second, so we can capture even the fastest CMEs. Somebody, do you have a question?
I was just wondering.
Yeah.
First of all, do you measure the charge state in either of these?
No, we don't. We don't measure composition, except we don't measure the charge state. The only species I'm going to show examples.
Protons and helium.
Protons and helium, yes. So protons and helium for the plasma sensor.
You mentioned that one of them covers part of EPAM.
But
how high in energy does it go?
The requirements for 2 MeV, they actually 6 MeV.
Oh,
yeah. So it doesn't go very far, but it goes to to the extent. But then we're overlapping with GOES. So our interest there is to basically make sure we have the continuity from plasma to GOES. Because with GOES we have 500 MeV, so we have significant coverage there. Yeah. And then in many of these, I'm going to show examples, but I'm starting to run out of time now. We have very fast, sufficiently fast measurements. 64 vectors per second with magnetic field, 2 seconds. The requirement is for 5 minutes, 300 seconds, but the actual performance is 2 seconds for the particles, and then 1 minute for the for the plasma, because we have to cover the entire distribution. But then if we need additional details, we can obtain them from research instruments. We don't need higher detail for operational purposes. And this is what I would like to mention here. So this is the layout. The spacecraft are not that large. It's basically the size of a very large appliance or a small car. And here, for educational public outreach, one of our artists has painted the instruments here. So we have the suprathermal-particle sensor on the top. This is actually the view of the spacecraft as it is viewed from the sun. So the Earth is behind the spacecraft, right? The largest part is the solar panel here. So we have most of the instruments are right at the top. We have suprathermals here. We have the coronagraph here. We have the plasma instrument here. This is a mass model because we're going to host an ESA instrument for X-ray radiance. But this was several years ago. It was decided to place it in the next mission because ESA was not, decided to provide that later. So there was not a problem with us because this was a guest instrument anyway, and we have that capability and very equivalent capability with GOES again. So we have sufficient coverage of the X-ray radiance on GOES. We can talk more about future missions, and then the magnetometer the magnetometer sensors are hosted on a 5.6 meter boom below the spacecraft.
Dimitri, sorry,
yes.
What is on the right? What is on the right of the plasma instrument? That it looks like a telescope.
That's the star tracker. It's a star tracker.
It's a telescope. So it is a telescope.
It's a kind of a telescope, yeah. So what are the developments? And this may be slightly, I think that's this is basically my AMS presentation from 2 weeks ago, expanded a bit. And this is in turn the ATU presentation. So SWFO, as I'm going to show you, was launched on September of last year. All the instruments have been powered on, all the deployments, the mag boom and so on, the high gain antenna have been completed. It has completed all the maneuvers. So in fact, it arrived at its orbit on January 23rd, so Friday of the week before last. And then, as tradition calls it within NOAA, it has been renamed. So from SWFO-L1, which was the name up until now we have to change. We have actually changed everything. It's called Solar L1. So Solar Observations to Advanced Readiness is a full acronym. And it's the first of a new sequence similar to GOES, which has now reached GOES 19 missions. We're planning for Solar 2 and Solar 3 starting in 2029. So in 2029, we'll have the Solar A mission, which will then, when it reaches its orbit, again around Lagrange 1, it will be called Solar 2. And in 2031, we'll have the Solar B, which will be Solar 3. The data have been collected by NOAA's network that I showed earlier. They're processed in real time by SWPC, Space Weather Prediction Center, and offline by the National Centers for Environmental Information. We're going through several tests, and I'll talk a little bit about these in a moment. And they will culminate at the initial operational capability, which will be declared on April 22nd. For those tests or reviews, we have 4 instruments and 2 reviews per instrument, at least in the first 2 cycles. 3 have been completed. And then we're including first public data announcements. So 3 out of 4 have been completed for the in situ instruments. We're also showing very good comparisons. So let me not dwell on this, but skip ahead. So shifting gears a little bit, I'll talk a little bit about the launch and first deployments, and then talk about the first few data. So it was a spectacular launch, very nice launch early in the morning at 7:30 on time. It was shifted by 1 day because of some SpaceX issue. It was launched on a Falcon 9 rocket together with IMAP and Carruthers Geocoronal Observatory. So 3 important missions, 2 by NASA, 1 by NOAA and NASA. And here's a video that may or may not have sound. I don't know if so this is the actual launch. And there are some views, I don't know if I included that show the spacecraft basically piercing the sun, basically going, So I don't know, was the audio heard online? From those who are online, was the audio heard of the rocket or not? That's always a question with Zoom. Yes. Hands. Okay, hands. Great. Okay, very good. Okay, now we're coming to the second test, so please pay attention. So this is actually a view now as SWFO or SOLAR-1 is going to separate. So this is the underside of the spacecraft. Imagine the three spacecraft I mentioned, SWFO-L1, IMAP, and Carruthers, attached to a long cylinder, which is called the stack. IMAP sits on top, and that was the first one to be separated. And the other two are placed on the sides, and they're ejected laterally. So we see this from the underside. So this is our magnetometer, as it's still stowed. And this is the magnetometer sensor. And this here is the solar array, now seen from below. And the instruments are on the other side, so we cannot see them.
So you can see it there.
And this is the audio.
There we go. That's that 4 revolutions per minute we were talking about. That is not
this is the Earth below us.
That is intentional.
And so this is IMAP, which is about to be,
have separation
this is the sun.
Of the IMAP spacecraft.
You will see the IMAP separating in a moment.
IMAP deploy confirmed.
And
there we go. IMAP has separated.
See it, but the camera
beginning
doesn't
its
see
mission
it
to map to the solar frontier and reveal how the sun shapes our space environment.
And now you can see it removed, right?
So IMAP.
So there's a small lag. Υπάρχει μια μικρή καθυστέρηση μεταξύ της εικόνας
και
του
right round. Right. Like a record, baby, right round.
Yeah, there you go.
I make all kinds of jokes here.
That's a great view.
Okay, so now let's shift to. Oops, hold on. Yeah, so we're moving now to SWFO.
Listening in.
And now that's the separation of SWFO. So now there's a different camera showing the SWFO spacecraft being ready to deploy, to separate actually.
SWFO-L1 deploy confirmed.
So they see it, and so the report is confirmed, and then here it is the
beautiful separation and successful deployment of the SWFO-L1 payload.
You can see
we're not done yet. We do have one more payload coming up. That's NASA's Carruthers Geocorona Observatory.
And later they had Carruthers.
We already
And so I think this is an interesting picture because for me, this is the last time that human eyes have seen the spacecraft, right? Since that time, we don't see the spacecraft. We just track it with radar and so on. So where is the spacecraft today? Or where was it on January 25th when I gave that original version? So I'll see if my cursor can show this. So here's the Earth from which the spacecraft came from. Our target is the Lagrange orbit, shown here. The sign is off to the left, obviously. And so there was a transfer orbit that all three spacecraft executed. In fact, all three were very close. NASA dubbed it the Cosmic Caravan. Το καραβάνι, το κοσμικό καραβάνι. They're great. So we have a good communications team and we collaborate with their communications team. So all that sounded great. But all three spacecraft, designed by different orbit specialists, were planned to take this very long transfer orbit, which is still on the ecliptic plane, largely, right? So they made several adjustments to their observations. And then it came down in this part of the orbit, and on January 25th, so Sunday, την αντιπροηγούμενη Κυριακή, στις 25 του μηνός του Ιανουαρίου, ήταν εδώ, στο επίπεδο της εκλειπτικής, και αυτή είναι μια άλλη όψη που είναι στο κάθετο επίπεδο, αυτό είναι το edge-on view. Στις καθημερινές συνομιλίες που γινόντουσαν, μπορούσαμε να δούμε πώς εξελισσόταν η τροχιά και πώς προχωρούσε το διαστημόπλοιο. Τώρα, so because of this lateral maneuver, there was a point at which the antenna, which is pointing to the sun, the high gain antenna, which is pointing to the Earth, could not articulate fully. This was known and decided on. So in order to communicate, to transmit the data to Earth, it was decided to have 12 hours per day of regular observations with the spacecraft pointed towards the sun, but the antenna would not be able to face the Earth. And then in the remaining 12 hours, the spacecraft shifted, it was rotated, so now it could face the Earth and the antenna could transmit the data, but now it was no longer facing the exact direction of the sun and solar wind. So So the data there do not represent, for example, the full solar wind profile. So as a consequence of that, for those limited times when the spacecraft was in that large loop that I'm showing there, we have these, for the plasma, for example, we have 12 hours per day coverage. For the magnetic field, we have full coverage, 24 hours per day. But then you can see there is a distinction between the agreement, for example, the data with IMAP, for example, which does not have that limitation. I'm just mentioning that to you so that if you hear, for example, that there was a certain limitation, this was very transient. It was very limited in time. And it was completed on January 2nd, right? So let's go to
This
some...
is a temporary situation?
Temporary, yeah. It was finished on January 2nd. And I'll show you some examples here so you appreciate that it was not a significant limitation. So let's go to some examples for the magnetometer, for example, which is shown here. And I think people know how significant an instrument the magnetometer is. And these examples will take the form of the first public announcement. So in these news releases, we have a highlighted set of observations that the agency selects to portray how good they are. And so this was, in fact, the interval around November 12, where we had the so-called Veterans Day storm. On November 12, there's a national holiday in the US called Veterans Day, ημέρα των Απομάχων. And during that time, we coincidentally saw a very large CME, in fact, two of them. So this is still before the storm, as it were, interplanetary space. We have the shock here, the sheath, and then the subsequent magnetic cloud. And then that is followed by a similar sequence in the second CME, which is more compressed. Those CMEs developed very rapidly, and when they reached Earth, they resulted in what's called the G4 storm, so a very severe geomagnetic storm with very good observations. Yes?
And how much earlier, how soon can predict the CME before coming to...
Right, so we saw that with LASCO, for example, with CCOR-1, which was already deployed from last year. And so we saw that, I'll show you, a couple of days ago. Yes, because even though it was fast, it was not as fast as the one that happened, for example, 2 weeks ago.
So we can take some measures,
Yes, absolutely, yes, right. That's correct. That's a very important part of our operation. So that's why we need the measurements to be completed in real time, so that we have as much lead time as possible. Yeah, that's a great question. Yep. And so on, this is the set of observations from the MAG for all three components. And then this is a set of indices, geomagnetic indices, showing the activity on the ground. So this is KP on the left, and it has been color-coded with a different index, the G index, which is a NOAA disturbance index. So whether in amplitude or color coding, you can see these effects, very strong storms resulting from these CMEs. So this is what I call the whale, because in terms of space weather disturbances, the CME is the blue whale of the disturbance that can happen. So the next view, let me go a little bit into detail. We'll come back to the whale in a moment. So this is another view of the quality of the data as I'm starting to wrap up. This here, for example, is a comparison between the inboard and outboard sensor. You cannot really see any difference. They're down to the details. One line is covering the other. And then on the left, I'm showing a power spectrum showing the sensitivity of the data in the frequency domain, showing the inertial scale, and even measurements down the dissipation scale. And there are more diagnostics that I'm not showing here. So we have a very healthy dialogue with IMAP, and also with using the data from ACE, showing how good our data are. And speaking of ACE, oops, that's the wrong direction. One of our validations is shown here. So these are actually two sets of measurements. So for every color, green, red, and blue, you see two lines. One is from our measurements, and with the diamonds with the same color, I'm showing the ACE measurements correspondingly. And even though the spacecraft are not yet at the same location, ours is still going towards L1, and ACE is already in its L1 orbit, we have an excellent agreement between the two spacecraft, and it's going to be even better because the two are going to be even closer. And we're shifting now to the plasma instrument, an electrostatic plasma analyzer. We have some of the same requirements I mentioned already. And this is the first official sort of portrait of that measurement, showing the energies acquired during a specific part of the orbit. This is now focusing in that whale, structure, looking at the belly of the whale, the stomach of the whale, that is the magnetic cloud. And for that, we had 12 hours of observations, right? Because we're in that diagram and that phase in the mission, we would not have a full 24-hour duty cycle, but we had only 12 hours. And we have very high quality measurements for the protons shown here and the alpha particles above in higher energy, from which we can obtain the moments of density, speed, temperature, and even extract dynamic pressure as the product of density and speed. So excellent quality data. We passed the first, as with the magnetic field measurements, we passed the first of these reviews that took place last December, and then the next one is planned for March 4, and then the data will be released to the world. Another example from the same exact interval. The moments are exactly the same as before, but now what these graphs show are a spectral review ordered by azimuth, and then on the right we see the beam of the solar wind in heliographic coordinates, elevation and azimuth, as it fluctuates in the field of view of the instrument. So sometimes it's at the center, but sometimes the solar wind is coming up from a slightly different direction. Again, very useful measurements of the velocity distribution function, VDF, that we can use for both research and forecasting purposes. Here are some more examples, actually, for the plasma distribution. These are two recent shocks from the latter half of January. On the top, we have the January 10 interplanetary shock, and then below have the CME-driven shock with the sheath and the magnetic cloud still evident. Now we have 24-hour coverage after January 2nd. And you see the very high compressibility here. So we're debating how to portray that. You can see that calculating the temperature, for example, will be very complicated because it's not an isotropic measurement. Because of the shock profile, we have to have basically two temperatures, one for the parallel and one for the perpendicular component to extract all the moments correctly. So some very good quality measurements. Now we go to the third, suprathermal particle populations, and we have several applications there. One is, for example, based on the earlier arrival of electrons and what they can provide us in terms of observations for solar energetic particles, shown here on below. We want to adjust the focus a little bit, and so we can have these precursors using the electron flux as a precursor of the far more damaging energetic particle measurements that are important for astronauts and for airline crews and so on. So having a delay, that's what these vertical lines show, having a lag between the arrival of the electrons that we measure first and then the arrival of the more destructive species, we can alert, similar to the power grid that you asked for, we can alert the space weather users such as astronauts again, or airline pilots for that. And I think some efforts are underway here with in Athens with Dr. Malandraki, for example, who's working on part of the Hesperia model and its UMASEP component. So they will be using these data as they have been using also ACE data. Another application shown here in the diagram showing the flux of the ACE measurements versus KP. That's part of a tool that's used within SWFO to forecast, at least roughly, this KP, so no details present, the level of activity on the ground with this empirical correlation between fluxes measured by ACE at about 50 basically kV and the KP index. So there is some correlation there. Anyway, what are the new measurements? They're shown here. This is actually the first light from this So I'll skip over that. We can go back if there are any questions. And this is actually the first publicly released image. We have electrons at the top. From that part of the detector, we have ions below showing the injection happening later on that day. That was October 22nd and 23rd. And then we added in that release, in that press release, the GOES measurements at a very high energy range to show, again, the prediction capability that this gives us with the early arrival of the electrons well before the 10 MeV or higher of the GOES observed particles. And on the left is another nice comparison showing the CCOR-1 observation, that's sort of a remote sensing versus in situ τηλεπισκόπηση και επιτόπου μετρήσεις, έτσι δεν είναι. Τηλεπισκόπηση με το CCOR-1 που βλέπουμε την διαταραχή να ξεκινάει από τον ήλιο και μετά τις επιτόπου μετρήσεις από το STIS που δείχνουν τις διάφορες ροές σωματιδίων, τα ιόν, τα ηλεκτρόνια και διαφορετικές ενέργειες. Οπότε έχουμε αυτή τη συνεργασία, we have this, basically this synergy between different parts of this program and other programs. So let me then start closing up with the item that's perhaps most of interest to you. When do you get the data? There is this process within NOAA, and there are similar processes in NASA for validating the data and the products that are derived from them. So for each type of product, we first go through the beta product validation review. Then we go through a second stage, which is called provisional. And then the third stage is the full, which happens typically 1 year or longer after the data have been vetted and reviewed extensively. So for for CCOR-1, obviously we went through these first two stages and the data were released publicly back in February of last year. And then for the in situ measurements, we also went through the first part of the cycle last fall, and we're about to start the second set of reviews in February and March, and that's when we will release the data to users. They will be accessible both in real time from SWFO and also from the archive at NCEI. At the same time, we also have first public releases similar to what I mentioned to you already. Any questions on this? Something like that sometimes. Okay, then one step closer, this is where one can obtain the data. So one can obtain the real-time data, as this example shows from SWFO. The archive data are stored, both the real-time archive data and also a second line of data called the retrospective data, calculated 3 or 5 days after the fact, are stored at the archive at NCEI, and this is how you can obtain those. And then for additional information on the mission, such as requirements, the instrument specifications, the papers that have been written about them, publications made, conference material, and so on, you can come to our website and visit, and browse through those pieces of information. So in summary, the SWFO program has been designed to provide these data to a variety of users, first and foremost the operational users, such as the forecasters, but then we keep in mind our retrospective users, namely scientists, such as this community, that can use the data for solar and heliospheric science. The mission has reached the L1 orbit recently and was then renamed SOLAR-1. And as we saw, all instruments have been collecting high-quality data. At the same time, I didn't mention that in much detail, the CCOR-1 door, the CCOR-2 door was open, and with the first light from that, we still have the data under embargo, so we don't show those data yet until they pass the first of those reviews, the beta review, as we called it. Then sometime in April, we'll actually release the data to the public. So we expect additional interest from the community, and this is partly one reason that I'm here, basically pass the message that the data are there for CCOR-1 and will be there soon for SWFO-L1, and welcome you all to using these data and asking questions on their various uses. So with that, I will close, but then I have to sort of, I can talk about an interesting science topic that I have data slides for if there's a question about the comparison of data from 6 missions around Lagrange 1. So thanks again for your interest.
for your talk. It's time for questions. First, audience here. If there are no questions, let's go ahead.
Just a comment. We have come a long ways from 1997 when the space weather real-time data on ACE was added last year, just before we launched the spacecraft, in fact. And it's now, I guess, going to be 30 years next year. But now we have such a wonderful fleet of data, very comprehensive, much faster in real time, and so we're kind of great. So I think the field is really blossoming.
Yeah, we're very lucky to have this. Yeah, and I can talk more, but that's what I was alluding to actually. One of the talks. Yeah, and I'll come back to that if you don't mind. That not right away, but in a moment. See if there are any other questions about how we can combine this data, because now we have many spacecraft around L1. But anyway, thank you for the comments, somebody. And any other comments?
From curiosity, for the computation of the trajectories, which dynamical system did you use? The CCOR-1 restricted three-body problem or elliptic restricted three-body problem for Sun-Earth system?
I don't have the details. I think I can direct you to. I can put you in contact with our team in Goddard that calculates these trajectories. But of course, there are many. And I don't remember the detailed answer to that. It's not my field exactly, but of course I think you're implying that they're using many more other bodies, right? It's not just three-body problem. They're using Jupiter. They're using basically all the large bodies in the solar system. I don't have that information, but it's available online. There are several papers that have been already published on that as to what they were planning to use a few years ago and what they've come through and used. So the name there is David Folta. He just recently retired, but if you look up David Folta and trajectory for SWFO-L1, there's a paper in the community that can provide light on this, or I can send you the paper.
Okay, it would be very nice. Yeah. Because I worked on this because the same Ross, but is an expert in this from Virginia Tech and has done a lot of work about this. And also the change for the orbits. Did you use McGee representation?
Which representation?
McGee representation.
I'm not familiar with that, sorry. But they will be able to answer these questions. So.
I guess all this goes to that correction they have to do from time to time to the orbit, and this will decide which is the preferable calculation stuff. Probably, I don't know.
Well, it's a question essentially about the multi-spacecraft analysis that somebody can do. Yeah. And is there a planning, of course we're going to talk about that as you said, but is there also a planning for providing, for example, combined data products with different missions? Is there sort of an agreement between different missions to do that?
Thank you. That's a great question. I'll use some slides. So I should have put them there, but I'll skip over some of these. This is another great example, a NOAA that SWIPSI did. I'll skip over that. But here we are. So we have to realize now, and we realized it sort of several years ago, there's this multitude of data from a multitude of spacecraft. And here we have SOHO, DSCOVR, IMAP, SWFO is very faint, SWFO, not SWFO-L1, and so on, and ACE. And all of them are revolving around this common Lagrange point. This is the view from the Earth towards the Sun. And to the right is the side view, and you can see the almost identical SWFO-L1 and IMAP trajectories there that led to these ellipses. And here's a calculation that was released just last Monday, a week ago, from NASA. If you go to their SVS, which is a great resource, να το δείτε αυτό γιατί έχει θαυμάσιες ταινίες και βίντεο, πιστεύω θα το ξέρετε, visualization system. This is a recent publication which shows these missions in a sort of 3D rendering, which shows how well they will be able to represent different scales in the solar wind. So this is a comparison, for example, in the distances between SWFO-L1 and IMAP. You see they're very, very close here in the beginning, and then even when they're around L1, they will be orbiting in still relatively close. And this is a histogram on the right of combining now 6 missions and finding all these spatial scales from the very small ones here on the right to the very long ones of the separation distance that they can explore, because some of them are in these very tight Lissajous orbits, and two of them, Wind and then Aditya, we also have an Indian spacecraft there, are in these halo orbits. So, and we also have these orbits, which I'm not showing here, I just have a schematic of a box here, showing that at the beginning of their mission, SWFO-L1 and IMAP were very, very close together, and they're down to 200 kilometers, which is amazing. I mean, to be close to L1 and measure distance at 200 kilometers. So that's why I would like these missions to go on as long as possible and not be turned off, even though they don't, you know, missions like ACE and DSCOVR, for example, have lived a sort of a full life. So there is planning. We just had a meeting on January 16 in Princeton with IMAP and Aditya, and we had other meetings last year. So the plan is to have a joint data set. We're not sure exactly who's going to host it, where we'll have all this data, magnetometer, plasma, and particles from all these missions, ideally, as many as possible, so that people can begin, as the saying goes, and obtain data for their analysis. Yes.
So is there an effort to compare the small scale that you find in in-situ data with features seen in the coronagraph? Okay,
that's exactly, yeah. There are signs. You're making me show more and more stuff. So yeah, there are many research objectives. So for example, one of the questions is, let me stay here. Go back. Yeah. So for example, let's stay with this because it's similar. I'll put on the various objectives. Here's the question: if we have 6 measurements, which one is the right one? Right? If we have 6 measurements, can we just average? Nobody would average, but would we somehow combine? So if we want, for example, to drive a magnetospheric model or an anospheric model with just one number, one time series, how do we construct that time series? This is not just a physics problem, it's also a combinatorial problem, right? In the heart of it, it's a physics problem, of course. Also, as these measurements move around, as these spacecraft move around, not only which one is the right measurement, but as they're probing these structures, a CME coming in, can we not reduce the measurements, but actually use them to reconstruct the structure of the CME, right? So these are very good questions, like the one you asked, what's the relation between these measurements and the coronal source of the drivers, right? That we can start asking, what's the relation between coronal and 1AU type of stages in the evolution of a structure. So the community has been asking these questions with imperfect or less perfect tools. This is not a perfect tool, but now having 6 missions or 5 missions, the number will vary, we can start answering these questions in a different manner. So lots of material for researchers.
Are there maybe some questions from the online audience? If yes, let's go ahead. I don't see any hand here.
I don't see anything in the chat.
Okay.
Can put up your hand. Okay.
Yeah, well,
I think we're over time also.
We hear that waving, but okay. Then, if there are no more questions, thank you very much again.
Thank you very much. Okay, we'll stop here then. All right. Anne, giusto con edit.